Okay, now suppose I have a surface S, and I would like to find the volume suppose I'm trying to find the volume where this projects the volume under that surface, which is z equal f of xy above the xy plane. What I do, I take this and I break it into m intervals, and I take this and I break it into n intervals. So I'm really looking at this rectangular region in which x runs between, what did I use, green, A to B, and y runs from C to some D. So this is the only region I'm interested in. So that region over there looks like this rectangular piece. We're picking a rectangle just to make things simple in the beginning. Then we're going to go in the next section to a general region. So what I did, I broke when we did the area on 2 dimensions, we had only one axis to worry about. Those should be rectangles. I'm not liking that at all. Here, I have a better idea. There we go. Something like this. And you'll figure this out quickly to pinpoint a point. So say that point right there. I'm going to call that x sub 1, y sub 1. This point right here, I'm going to call that x sub 1, y sub 2. This point right here, that's going to be x sub 2, y sub 1. So you notice if I pick a general point, I'm going to call this x sub ij, y sub ij. We call him star because you could pick it anywhere you want, and I'm referring to one specific rectangle in there. Well, would you agree that the volume is going to be that right there? Pretty much top minus bottom. So I'm now writing everything that I just mentioned. Let S be a solid that lies above the region R. This is all of this right here is region R, or all of this right here region R. Under z equal f of x, y, z, it's right there. If I have z running between 0 and the actual surface, so between the floor and the surface, where x is between a and b and y is between c and d, then the volume is really the sum of those. Basically, it's area, the base, times the height at that point. So take this point, run the height up, multiplied by the area of the base, because that's what volume is. It's area of the base times the height. And I could write those in a general case. And if I choose those to have a star, meaning they could be anywhere in that region, then I could apply the Riemann sum and say, look, if you want not an approximation, the exact volume, take the limit as m and n approaches. Okay, I just need to change one thing in there. I made a small alteration right before I started this. Here we go. Much better. And we know the limit as n approaches infinity will give you an integral, so that's going to be the double integral over region R. And that's the idea. Fairly simple. I could have spent a lot longer on it, but it doesn't really come up, and we don't need to really go into the theory as much, just to grasp the idea. And pretty much this is the deal right here. If f is continuous, that's the only condition throughout the rectangle, then the double integral, remember, with any area I could take a delta x or I could take a delta y, just like you did in 5a, if you remember, or your 1140 class. I could integrate with respect to x first, then y, or y then x. In this section, it's not going to make much of a difference as far as the limits, because that's a rectangle. And we're going to play with this on both fronts. So first, we want to make sure we understand what we're doing now. We're integrating with respect to x the same function than with respect to y. If I'm integrating with respect to x, you're going to treat y as a constant. So as far as y is concerned, you ignore that. That's x squared over 2 evaluated from 0 to 2, and you just drag the y squared as a constant. So that's y squared over 2 into 4 minus 0. That's pretty much 2y squared. And if I was to integrate with respect to y, then x is a constant. You ignore the x, and you'd say that's y cubed divided by 3 evaluated from 0 to 3. So that would be x over 3 into 27 minus 0. That would be 9x. So separately, that's really what they look like. But if I put them together in my example 2, and I said, here, why don't you integrate x with respect to 0 to 2, and the y from 0 to 3, pretty much what I did up there, you'll notice now things will be slightly different. If this is positive, this is volume. We know an integral finds more than that, but for now we're focusing just on volume. So what would this be? This will be, you would work this out first, just like we did. With respect to y, you would say that is x y cubed over 3 evaluated from 0 to 3. That is x over 3 into 27 minus 0. So that's pretty much 9x. Now, you take the 9x and you apply the second integral on it. And that would be 9x squared evaluated from 0 to 2. That would be 9 into 4 minus 0. That would be simply 36. And if I was to take this integral and switch the order, do a dx first, dy after, you'll notice it wouldn't make much of a difference if I take this part out first. With respect to x, that's x squared, y squared evaluated from 0 to 2, y squared over 2. That's y squared over 2 times 4 minus 0. That is 2y squared. Now take the 2y squared and integrate that from 0 to 3 with respect to y. That is 2y cubed over 3 evaluated from 0 to 3. That's 2/3. Throw the 3 in, 27 minus 0. 3 divides 27 9 times, and you get 80. Okay, I messed up somewhere. Where did I mess up? Just let me check really quick. Found it. When I integrated the x, that should have been over 2. And that would make this 18. There. So it doesn't really matter how you integrate this as long as you integrate it properly. So we're going to play with this a bit. In the beginning, they're kind of walking you through. So what are you going to do here? You're going to work this out just like we did. You're going to say, well, let's do this part first. With respect to y, this is y the sine of x plus the sine of y evaluated. Remember, this is y equal to y equal. So as far as x is concerned, this is a constant. So that would be pi over 3 sine of x plus sine of pi over 3 is really what's that? Radical 3 over 2. Minus, you throw the 0 in, well, that's a 0. So all what I'm left with is pi over 3 the sine of x plus radical 3 over 2. Now I take this quantity and I say, alright, let's take pi over 3 the sine of x plus radical 3 over 2, and let's integrate that with respect to x, where x runs between 0 and pi over 4. And that would be negative pi over 3 the cosine of x plus radical 3 over 2x evaluated from 0 to pi over 4. That will be negative pi over 3 times, that's radical 2 over 2, the cosine of radical of pi over 2, plus radical 3 over 2 times pi over 2, minus, when you throw the 0 in, you get negative pi over 3 times 1 plus 0. So my final answer will be negative pi radical 2 over 6 plus radical 3 over 4 pi plus pi over 3. You can get a common denominator, factor a pi out, you know, you could have a lot of fun with that. Now on a test, this is all I want. Once you get me the actual values, leave it alone and move on. And if I was looking at this problem, say, alright, well, let's see. This right here, with respect to x, that's y e to the x evaluated from 1 to 4. That is y into e to the 4 minus e to the 1. Alright. Now take this quantity and with respect to y from 0 to 3, that is y squared over 2, and this is just a constant. Remember, this is y equals, so this is e to the 4 minus e to the 1 over 2 times, throw the 3 in, that's 9/2 minus 0. Again, on a test, this is all I want. That's really 9 into e to the 4th minus e to the 1 all over 4. There it is. It only requires techniques of integration. Now, the next set of problem, they give us the region. Now, it doesn't really matter which way you go. The only time you might want to switch the limits on the integral when you notice you're trying to integrate, and this is very hard to do. So if you went in order, if you said, let's go dx first, then you're saying the inside most integral is running from 0 to 2. Then dy, now you're saying the outside most integral is 1 to 4. That's a must. So that part you can't mess around with. And if I'm integrating with respect to x, well, that's simply x squared over 2y plus x radical y evaluated from 0 to 2. That is, again, dx. That is 4y plus 2 radical y minus 0. So that's pretty much it. That is 4y plus 2 radical y. And now I'm going to integrate this with respect to y from 1 to 4. And if you switch those, you get the same thing. That's not a problem. This is 2y squared plus 2, add 1 to the power, divide by that, 1 to 4. That's really 2y squared plus 4/3 y to the 3/2. Evaluate from 1 to 4. That is 2 times 16 plus 4/3. If you square root y, you get 2. Cube it, you get 8. Minus, put the 1 in, that's 2 plus 4/3. Again, on a test, this is all I want. You don't need to go any further. For the homework, you really want to match it with the back of the book. So that is 30 plus 28 over 3, or simply over 3, 90. 90 plus 28, that's 108. 118, same thing, right? And that would be the answer in the back of the book. Now I'm going to stop this video here and pick up in the next video.